So get ready to learn some vocabulary for distributions, to describe distributions of a histogram. Now, first of all, I want to show you that oftentimes we'll make a curve along distributions. So even though we may have a histogram that looks something like the following, we would just try and draw sort of a curve along it to simplify it in our drawings. And if I have a distribution that looks something like this, this is a skewed distribution, and it's skewed left. Of course, if it looks something like this with a long right tail, then it is right skewed or skewed right. And here we have some of a symmetric distribution. Another way to describe these is using mode. Mode is the most common data point, and we'll go over that later. However, right now we know that whatever data point is right here, whatever is the tallest point of our distribution, that is the mode. And all of these are what we call unimodal. They all have one highest point, and therefore they call us unimodal. If you have distributions that look something like this, where we have what we might call two modes, this is what we call a bimodal distribution. And if you have anything more than two modes, such as something like this, we would call it multimodal. You could also have a really boring data set like 1, 2, 3, 4, 5, where our histogram would basically look like this. This has no mode, and again we have frequency on our left, and we have whatever x value, whatever variable we're looking at on the right. Could be movie earnings and millions of dollars. This is what we call a uniform distribution, and it could be slightly off, but it would still be approximately uniform. Probably the most important distribution that you'll see is a distribution that looks something like this. It has two tails, it's unimodal, and symmetric. And when you see a distribution that looks like this, this is what we call the normal distribution. Okay, there are a couple of ways that we could find the center of the data. First, what I would like to look at, well, let's go ahead and graph this data real quick in a histogram. The histogram may look something like this, and if I were to draw a curve through it, it would be represented like that. This is right skewed data. It's definitely unimodal, and the mode, the most common data point, is 1. But my question is, where is the center? And there are a couple of ways to look at this. And one way to look at this is to see the actual midpoint of all the data. The midpoint of the data is called the median. So here we have 1, 2, 3, 4, 5, 6 data points. And so if I were to point to the middle of the data, there's actually no middle center data point. If there was, that would be the median. But since there's not, we're going to take the midpoint of 1 and 2, or the average of 1 and 2, which is 1.5, or 3/2. All right, that is the median of our data. The mean, we need to add up all of the points, the data points, and divide by the number of data points. the number of data points we call n. Adding up all the points, we use the notation sigma, which is a capital Greek S, and if we add up all of the data points and divide by n, or the number of numbers, we get 2 5/6, or approximately 2.83. So our median here is 1.5, our mean is 2.83. So pause for a moment and think about why our mean is so much higher than our median. If you thought that it's because of this value 10, you are correct. This value could be thought of as somewhat of an outlier, and therefore it's pulling the mean, or the average, which are synonyms, higher than our actual middle number. If you think about the relationship between mean, median, and mode when you have skewed data, for example, in this case we have a right-skewed distribution, and we know how to identify the mode. The mode is sort of the tallest point of this distribution. So this point right here is identified as the mode. Right here, the last two, one is the mean and one is the median. I know that the mean will be pulled to the right of the median when you have right-skewed data, just like we saw that 10 do. So let's think about what kind of data may be right-skewed. Well, some things with that have a floor, meaning that you can't have less than 0 children. So you may have a lot of people have 0, 1, 2, 3 children, and very few people have 8, 9, 10, 11 children. Again, perhaps gallons of water per month used. There may be some areas that some people use quite a few gallons of water per month, but most of us are down here. House prices are another variable that a lot of people use the median for, and that's because if you have multi-million-dollar houses up here, it really pulls the mean up, whereas most of the houses may be right around here. So what about a left-skewed distribution? First of all, what kind of variables may be left-skewed? Well, if I gave you all a multiplication test, hopefully that would be left-skewed. Almost everybody would get them correct, hopefully 100% on your multiplication table. Some of us may not remember it as much as others. All right, so we have our mode would be very high, our median would be very high. However, maybe some people missed the test and got zeros, or a few people never memorized their multiplication table. That may bring the mean down. The mean is pulled to the left when you have left-skewed data.
If you have normally distributed data, unimodal, symmetric data, then your mode is in the center at the highest point, and it's equal to the median, which divides the data in half, 50% on each side, which is equal to also your mean, which is sort of the balance point of the data. The mean is not resistant to outliers. So, for example, if the mean student income in my class of, let's for example say of 50 students is $12,000, then let's just say somebody really rich decides to take my class. Let's say Bill Gates decides to take Math 11. So he's my 51st student. So the prior mean was
y bar, or the sum of all the y values, the sum of all the values of the income of each student in my class, divided by 50, which is 12,000. Well, let's say if Bill Gates makes, I don't know, 500 million a year. I have no idea how much he would make in a year. But if he joins our class and he makes that much money, the new mean is 9,800,000. The median probably stayed about the same. Maybe moved over one value, right? The median was about the same, but the mean went from 12,000 to almost $10 million. And by the way, let's just say he made $5 million a year, it goes to like or $50 million a year, it goes to like $1 million. So the idea is the mean is not resistant to outliers. However, a median, that would only change maybe one value over or something like that, because it's just the middle value, right? Adding one more value to the end doesn't change the median. The median is resistant to outliers.